I always believed that neural networks were a way for us to study intelligence, both in the brain and in artificial systems. I think that when we talk about intelligence, we do have to talk about norms, by which I mean some metric that says this is good, this is bad. When you think about actually trying to replicate what humans can do, it seems crazy not to at least in part consider what's happening in the brain. We are a 40-watt machine. Our brain is a 40-watt machine.
Okay.
Our whole body is a 100-watt machine. And yet we have, more parameters still, quote unquote, more synapses than the biggest artificial neural networks. Do you really want to arrive at the situation where, say, a decade from now, 50% of the electricity consumed in our societies is consumed by AI data centers?
Mhm.
That would be awful. AI would be symbiotic towards us. And I think in particular, as we move towards quote unquote super intelligence, meaning AI systems that can reason even better than we can, the danger comes not from a super intelligent system, but actually from a really dumb system. And this is where I would fear potential downstream effects from AI is if people put AI systems in charge of, you know, deadly weapons systems, or even they just give them a lot of power to manipulate various other components of systems that could eventually be deadly.
I'm here at the Mila with Dr. Blake Richards. Welcome.
Thank you for having me.
My pleasure. So you're a researcher here at the Mila. You're also a professor, associate professor at McGill. Is
Correct.
that right?
Yes, I'm an associate professor with a joint appointment in the departments of computer science and neurology and neurosurgery.
Okay. And you study neuro and AI.
Correct.
Okay. What is the specific realm of that domain that you're looking into?
So I am a bit academically promiscuous, let's say. There's no specific realm that I focus on other than the broad intersection of neuroscience and artificial intelligence. The way that I like to describe my lab's research program and my interests more broadly is that I'm very interested in general principles of intelligence. So, what constitutes appropriate, intelligent systems behavior, whether it be in an artificial system or a living system? And I do personally believe that there are very general principles around what makes an intelligent system, what sorts of problems intelligence requires us to have a solution to. And these are the sorts of things that my lab studies.
Wonderful. So I love to get into all the AI stuff, what intelligence means, right? And find out more about that. But first, what is really the thing that got you into studying? You've obviously studied neuroscience. You studied in computer science and
I did. I started in computer science.
Okay.
Yeah. So I did my undergraduate degree at the University of Toronto
Okay.
back in the early 2000s. And at that time, I think there still is, but there was a program at University of Toronto called Cognitive Science and Artificial Intelligence. And it was basically 50% computer science and then 50% a mix of psychology, philosophy, and linguistics.
Okay.
I was able to combine that with a major in computer science as well because it was so many computer science degrees. So I actually got at the time we called it a double major in cognitive science and artificial intelligence and computer science. So it was like really mostly computer science, but with these additional bits of linguistics and philosophy and psych.
That's an extremely interesting program. I would have loved to have taken that.
Yeah, honestly, I loved it. It was a wonderful program. I learned so much from a variety of different domains. And I was also lucky in that at the time, University of Toronto had some of the most fascinating and important people in these fields. For example, I had the privilege of taking computational complexity with Stephen Cook, the guy who came up with the P versus NP problem. And then I got to take neural networks from Jeffrey Hinton. And that was actually how I got into neuroscience. So I took Jeff's neural networks course and loved it because I had actually found, though I enjoyed the program a lot, I would say that the courses I enjoyed the least in the program were the artificial intelligence courses that I received at the time. Because at the time, artificial intelligence courses consisted mostly of basically logical programming. So, for example, the Intro to AI course I took in 2003, we did like prologue programming of basically like logic trees for sorting out deliveries to factories or something like that. And it was pretty boring, and it also felt like, come on, this is never going to work in the real
Yeah.
world. And indeed, it never worked in the real world. Um, so I always found that a little bit frustrating. I instead enjoyed much more my courses in straight computer science, like computational complexity and stuff like that, until I encountered neural networks. And then when I did neural networks, I was like, this stuff really cool. And I was convinced both that it was the ticket towards building AI and that it would help us to think about computations in the brain more broadly. So I started to get more interested in the brain itself. When I graduated from undergrad, my wife and I had a deal where she would go do graduate work for a while and I would work. So I went out looking for a job, and my original plan was to work as a software engineer. But then I found this job at the Center for Addiction and Mental Health in Toronto, um, where they needed someone to help them analyze MRI scans, because basically a bunch of psychiatrists had collected all these MRI scans and had no idea how to analyze them. So they needed I called myself their math and computer monkey. I was there to basically like, they would be like, here's what we want to measure. And I would have to figure out how to measure it from the scans. So I
And
did
those
that.
scans aren't easy to
And those
handle.
scans are not easy to handle. But my experience with machine learning, courtesy of Jeff, because I also spent some time working as an RA with him in his lab,
Okay.
helped immensely for doing that kind of work. And I enjoyed it enough that I decided, actually, I want to go into neuroscience. So I ended up finding a program which was fairly unique at the time at the University of Oxford, that it was called the 4-year DPhil in neuroscience, because PhDs in the UK are normally 3 years. But the first year of this 4-year DPhil was a catch-up year to allow people who had not done neuroscience previously to come and learn neuroscience, which I needed, because even though I did some psychology and stuff in my cog sci classes, I knew nothing about the biology of the brain, like zero. So I spent a year in the first year of my DPhil just getting caught up to speed on all of the basics of neurophysiology, which was a lot of fun. And I profited immensely from it, so much so that I decided, yeah, I really want to do neuroscience research. So that's how I got into neuroscience. I ended up doing both of course, my DPhil in neuroscience and then my postdoc in neuroscience. And then starting a neuroscience lab in 2014. But it just so happened that at the time that I was starting my lab, deep learning took off. And so, as someone who was always interested in those questions, and like I said, I always believed that neural networks were a way for us to study intelligence both in the brain and in artificial systems, I sort of redirected my neuroscience lab towards this intersection between neuroscience and AI. And I'm glad I did. It ended up being the right choice for a variety of reasons.
For sure. And you had the right intuition like years before as well.
Yeah, I was lucky that way. It helped that I was surrounded by really clever people who helped me build my intuitions on this stuff. Jeff was one of them. The other one was a guy who I was in this same undergraduate program with, named Timothy Lillycrop, who is a close friend of mine. And we basically bonded in our undergraduate degree over like agreement that most of the AI we had seen to date was shit, except for the stuff that Jeff showed us. And my conversations with Tim were, in large part, helped me to form my intuitions around these questions for up until today and moving forward as well, I'm sure.
For sure. So you talk about these principles of intelligence.
Yeah.
And I was listening to another podcast you had done, I don't know if it was a few months or a year ago, and you had discussed what intelligence means, because I think first we should define like what that means. But
Yes.
you had a really good analogy to or definition in regards to certain norms and like social norms with artificial intelligence.
Yes.
So could you expand on that and what it means for something to be intelligent and therefore what artificial intelligence would entail?
Right. Yep. So I think that when we talk about intelligence, we do have to talk about norms, by which I mean some metric that says this is good, this is bad.
Mm-hmm.
And I think that we can articulate intelligence more broadly as being a property of a system that is able to ensure that the actions that the system takes in the world will lead it to get better according to the norms that it has. And I view that, in a fairly broad sense, because you can get better and you can achieve the goal, like the norms you have in a variety of ways. One is to have explicit goals, and then intelligence is about figuring out how do you achieve your goals, what actions are required to achieve your goals. But there's also maybe less sophisticated, but still powerful, we can say habitual forms of intelligence that are about achieving your goals simply through automated reflex like stimulus response processes, but which will still, according to some norm, make you better at achieving that norm.
Mm-hmm. Right, right, right. And then you had made an analogy to computer science and what that really relates to. You were mentioning, I forgot what the exact quote you had said was
Well, so maybe what you might be thinking of is sometimes when I try to provide a definition of artificial
yeah.
intelligence, one of the things I say is that, artificial intelligence is necessarily the the field of computer science that is concerned with replicating the cognitive capabilities of human beings and expanding potentially on the intelligence that our cognitive capabilities afford us.
Mm-hmm.
And this is important as a definition because, look, all of computer science is about getting computers to do useful stuff,
Right, right.
right? So, like, is it artificial intelligence when we design a better operating system? Arguably not. Like, we consider that a separate domain because there, a better operating system is not equivalent to in any way replicating human cognition and the nature of human intelligence.
Mm-hmm.
And so I think that that's maybe an important thing to highlight is that generally when we talk about artificial intelligence, we're actually doing it in reference to human intelligence. Even when people talk about super intelligence or AGI or anything, I think they are still necessarily referencing human intelligence in their conception of it
Mm-hmm.
because they are interested in the particular forms of intelligence that, at least in part, overlap with our cognitive styles.
Right. And so that's why you think it's so important to study, I guess, the brain and try to replicate those systems.
Absolutely.
Because I mean, our definition of AI is based on, our human intelligence.
That's right. Exactly. So, it's worth saying that um, if you look at the history of artificial intelligence, this definition has always been there, actually.
Yeah.
So the term artificial intelligence was coined when some researchers back in the 50s organized a workshop in Dartmouth, funded by the NSF, where they said you can still find their proposal online. They were like, we want to look at how to get digital computers to replicate various aspects of human capabilities, human mental capabilities. So language, reasoning, all this stuff. Um, and they were very clear about the fact that they were replicating human cognitive abilities. But what's interesting is there has been, from the first get go, from this first workshop where they coined the term artificial intelligence, a split in the research community between those who believe that you could replicate intelligence purely by trying to replicate the computations that occur uh, in the brain, by which I mean like literally replicate our behavior without worrying about underlying algorithms that implement those computations.
Mm-hmm.
And then the field of people, like the subset of people who said, no, we need to also think about how the brain implements those algorithms that allow us to have these capabilities. And One interesting little fact that way is that first conference on that first workshop on artificial intelligence, they explicitly excluded the people who felt that we needed to replicate the algorithms of the brain,
Yeah.
and instead just brought in people who said, no, 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 we're going to program this all from scratch. Um, and that set up the whole division between what now is referred to as good old fashioned AI, the kind of stuff I learned in 2003 using logic and research and all this kind of stuff,
Mhm.
and modern deep learning systems, which are rooted historically in that other sector of people who said, no, 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 we should pay attention to the algorithms of the brain.
I suppose then you were kind of part of that second subset because you kind of noticed that, right, the neural networks were probably very important. You ended up
Absolutely.
researching neuroscience, and
Yep.
I suppose that.
That's right. Like this was the intuition that Tim and I built from learning from Jeff, basically,
Yeah.
was we were convinced that like, oh, when you think about actually trying to replicate what humans can do, it seems crazy not to at least in part consider what's happening in the brain
Right. Right.
and think about how that could potentially guide the development of our own algorithms. And this was, key to the development of artificial neural networks, because, let's be clear. So to make my language a bit less murky, I'm using terms here from Mars levels of analysis. So this is the idea that when you study a computational system, you can talk about the computations it performs,
Mhm.
or the algorithms that implement those computations, or the physical system, the physical substrate that allows those algorithms to operate.
Mm.
And I would say that I've always been convinced, and this was the whole idea behind artificial neural networks, that we can and should think about the algorithms happening in the brain, even if the physical substrate level is not critical for us in the AI realm. And
Mhm.
I think that intuition that researchers like Jeff and others like Rumelhart and McClelland and everyone who are part of the connectionist and parallel distributed processing group in the 80s, that intuition that they had that, look, we don't have to worry too much about the low level biology, but we do have to think about the algorithmic level,
Right.
was dead on, and clearly has been vindicated
Yeah.
in the success of deep learning.
For sure. For sure. Do you think eventually we'll have to move towards a more fundamental and like, biological level of implementation to really get that the next, I don't know, advances in the field?
Right.
Do you think that we're in it's a pretty good enough intuition to stay at the algorithmic level?
Yeah. It's a really
It's not.
important question, I think. So my feeling is that we can and should continue to maybe push a little bit on some of the implementation level stuff, particularly when we're thinking about developing more energy efficient AI systems.
Okay.
So one of the things that I think has been a shift in mindset for me anyway, and I think a lot of researchers in AI, is that, you know, when you look at what was the game changer for deep learning, it was GPUs, right? Like
Mhm. Mhm.
neural networks have been around since the 50s.
Yeah.
The particular form of neural networks that we use now has basically been around since the 80s. There have been some small updates to the
Yeah.
systems, but it's the core ideas were there in the 1980s. But the problem was we never had compute that allowed us to actually run these systems in parallel. And as such, when I was programming neural networks by hand in the early 2000s, like it was really slow because you were running this on CPUs. So
Mm.
like it was ridiculous how long your neural network would take to train. Um,
I can imagine.
yeah. So the shift to GPUs had a huge impact and was what really permitted deep learning. Now, the reason I bring this up is what's interesting is as the mental shift I was gesturing towards a moment ago is that for a long time, many people, myself included, assumed that AI researchers wouldn't have to worry about the hardware level because
Right.
you let the engineers do the hardware level, we worry about the software level. But really, what we've seen is that the hardware matters. The
Yeah.
hardware is what determines which algorithms will actually work at scale.
Mhm.
And as such, I think we have to come back to thinking more and more about hardware and AI. Many people are. I'm surely not the only person saying this. But then that presents an opportunity for also getting a little bit more inspiration from the biology for thinking about, well, how does biology implement these algorithms? Could we take inspiration on that for building new types of hardware?
Right. So are these big OpenAI data centers, are they just like one big brain almost in a sense that
To some extent, they are. That's right. But they're a brain that is ultimately massively less efficient than our own, right?
yeah.
This is the key point. Like the human brain is like,
All of us were taking that much energy.
oh man, it's
Energy.
crazy, right? It's crazy. Like we are a 40-watt machine. Our brain is a 40-watt machine.
Okay.
Our whole body is a 100-watt machine. And yet we have, more parameters still, quote unquote, more synapses than the biggest artificial neural networks they're training that consume, the energy of a small state over the course of a month or something like that for their training. So it's orders and orders of magnitude different in energy efficiency. And that's where, even though we've at least cracked the parallel problem with GPUs, we haven't cracked good efficiency. And I hope to see that cracked. Maybe it will involve biological insights. Maybe it won't. I suspect the next 10 years will show.
Okay, so I guess that's the next challenge, next big challenge for AI in general. I guess it kind of does that kind of go against the scaling laws in a sense that just throwing more compute at a model might, help it.
So I don't think it goes against scaling laws because I think that there is just a fact that throwing more compute at problems helps.
Yeah.
And that's one of those principles of intelligence that I would articulate. Like that is a general principle of intelligence. It applies to any system. It's why the human brain is so stupidly big, right?
Yeah.
Because just throwing scale at the problem does actually help. But like, and let's be honest, the human brain would probably be even bigger if it wasn't for the constraint of passing through a birth canal. Like evolution probably would have kept cranking up that knob on the number of neurons. And that's why, elephants and dolphins actually have bigger brains than us by a fair whack. And I also suspect they're smarter than us. But that's a whole other conversation.
Interesting.
Anyway, the point is that cranking up the amount of compute is a perfectly viable strategy and it works. But more the issue with efficiency is, do you really want to arrive at the situation where, say, a decade from now, 50% of the electricity consumed in our societies is consumed by AI data centers? That would be awful. Like we already have constraints on the amount of energy we're going to need, especially as we electrify our transport systems and all these other things. So if AI researchers can figure out how to make their systems more energy efficient, that would be of huge benefit to society at large, I'd say.
No, for sure. And so for your lab specifically, what is is there a specific goal or mission that you're trying to, work towards? Is it something like, grander, AGI, some kind of general intelligence, or really uncovering those principles of intelligence and, structuring it in a way that it helps other people understand what it is we're actually working with here?
Yeah, it's more the latter in the case of my lab. So we, as an example, one of the principles of intelligence that I've always
could you list them as well? Like, are there?
I can give some examples. So one principle of intelligence is that intelligence requires a solution to the credit assignment problem. So what I mean by that is the credit assignment problem is basically the problem of if I take some action or if I have some pattern of activity in my neural network and that leads to a good or a bad outcome, how do I actually figure out what changes to the network or to my actions will lead to better outcomes in order to maximize that norm that we discussed?
Right.
So
the back propagation and
so this is what backpropagation solves for us. So in the case of artificial intelligence, we use backpropagation of error as our credit assignment mechanism. And then for action-based credit assignment, we use reinforcement learning mechanisms. In the case of the brain, I think it's safe to say that though there's still a lot of work to do, we've determined that in many ways, the brain does seem to use reinforcement like systems, like reinforcement learning like systems for doing action credit assignment.
Mhm.
The exact principles by which that happens in the brain are still being uncovered, and it's something my lab contributes to. But then there's also the question of how do we solve the credit assignment problem for neural activity patterns and synapses, which is what we use backprop for in AI. And we don't know how the brain does that. So one of the things that we work on in my lab is indeed trying to think about, okay, how might the brain be solving credit assignment problems?
Okay, okay.
Another example of a general principle of intelligence, in my opinion, is the question of um, how to best use memory, that is information transmission over time, to guide your actions in the future. Because there's a non-trivial problem here in terms of like, most of the information that you encounter in your life is not going to be relevant to actually guiding your actions.
Mhm.
Uh, and so exactly what sorts of memories you should store, how those memory systems should be structured.
Right, because we don't remember everything, right?
No, that's right. And moreover, even when you look at our quote unquote episodic memory systems, so like the hippocampus in mammals, not just mammals, I guess, in many vertebrates, what you see is that even the hippocampus itself is not some kind of perfect snapshot of things that have happened. It's actually its own generative model. It's
Mhm.
building something like a model of what's happened to you in the past. And so thinking about like, okay, how do you design a model of your past that maximizes your capabilities in the future to meet your
Mhm.
behavioral goals is another principle of intelligence that has to be addressed by an intelligent system in which we study in the lab.
Okay. So how many are there of these principles like nailed down?
We haven't done a big list. That might be a fun exercise at some
Yeah.
point in time. But I think these are some of the examples of this. Other principles of intelligence that I think are relevant, which we study in the lab, and which others study as well, are, how do you um, get good coordination between multiple agents towards cooperative goals? That's another key component of intelligence. Like if you are an intelligent agent, arguably there's a big difference between an intelligent agent that is incapable of cooperating with other agents and an intelligent agent that is capable of cooperating with other agents. And those that can cooperate will be ultimately a much more intelligent uh, system because of their collective intelligence. So
Mhm.
understanding how to cooperate is another key question and a sort of principle of intelligence, let's say. Um, then there are other examples. So, another one that we're interested in is the question of what should the structure of representations be in a distributed system in order to maximize your ability to generalize downstream.
Okay, okay.
So we do some work in this area on like what are the structures of representations that
Like the
seem
low
to
level representations of memories in some sense, or that we
memories or images or
yeah.
text, whatever you want. So this was actually work where we were directly inspired by brain. So
Mhm.
there was a beautiful study by a neuroscientist named Carson Stringer, and she did this interesting study where they looked at the dimensionality and the geometry of representations in mouse visual cortex,
Okay.
and they showed that the specific structure that holds in the brain, like with respect to how high dimensional and how smooth the representations are
Mhm.
in the mouse's brain, um, it sits in this Goldilocks zone where not it's not actually very low dimensional and it's not very smooth, but it's also not total chaos. And it's not just a really high dimensional
Yeah.
hyperfractal system. Instead, it sits somewhere in between. And so a student of mine named Arna Ghosh did this wonderful study a couple of years ago with some of his friends, where they showed that actually you can show in deep neural networks that are well trained, they end up developing similar representations in this Goldilocks zone where they're just high D enough and just unsmooth enough, but still low D enough and smooth enough that they permit good generalization. And so we've been following up on this and now studying it not just in vision models, but in language models and other things. And
Mhm.
that's another example where it's sort of, we're trying to get at principles of representation and generalization that we believe apply equally across real brains and artificial brains.
Right. So I suppose you can like validate certain concepts that computer scientists maybe are developing, and at the
Yep.
same time take from the neuroscientist research and try to apply those into a new, representation or
Yep.
system for the model itself.
Exactly. Exactly.
Interesting. And I also wanted to talk about AGI in general and what
Sure.
um, this push towards a general form of intelligence. There's a lot of skepticism and also a lot of fear with AGI coming about and this chaos situation. But I was listening to your conversation on that podcast, and you were mentioning that you're very skeptic of this kind of circumstance actually happening. In regards to AGI is not going to wipe us out of the earth.
Yeah.
They're not gonna. It's not going to be the apocalypse. But from a very biological standpoint, so what's the argument behind that? Like, why are you not scared that tomorrow there's going to be a
Yeah. So, my argument for this, I think it's worth clarifying that my argument is really around this question of human extinction or near extinction. That's the thing I'm very skeptical of. And the reason is actually fairly simple. I do not, so when you look at evolution and biological systems, um, although sometimes there is competition between species, most of the time there's symbiosis between species because that's what evolution promotes is stability and symbiotic relationships. Ecosystems where every species has their particular niche within the ecosystem. And, if I'm like a tree, most of the species that I interact with are helping me.
right?
They help me to reproduce. They and I help them. I provide them with food and shelter, and this is the core of most interspecies relationships. The only time that you see very direct competition and one species basically wiping out another species is when they occupied basically the same niche.
Yeah.
So when you've got say two groups of primates that are basically all for all intents and purposes the same, and so then they have a conflict and one might wipe out the other. So then when we look at AI, the question is, would we be in any way competing for the same niche as AI? And here's where I just don't buy that. I don't buy that. Like, I think that when you look at what AI's relationship is to humanity, it's far more likely, like way, 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 infinitely more likely, in my opinion, that ultimately the relationship would be a symbiotic.
Almost perfectly like complementary.
That's right. Like a tree, we provide AI with food and shelter for all intents and purposes.
Yeah.
The AI cannot exist without us. Now, like, this is where, it's been interesting for me because I've had a bit of divergence from Jeff Hinton, for example, on this question. And when I've spoken with Jeff about this, I've said this to him and he said, oh, well, but if the entire economy is automated, then they are competing with us for resources. And I suppose he's right, but that's where I'm skeptical of the full automation of the economy. I don't think that's anywhere close to being a reality. Like, if that's going to happen, it's still not going to happen for decades.
Yeah, that's like AI essentially making its own, like electricity. Everything that we have today is
That's right.
run by
Exactly. Like,
system.
it's worth emphasizing that robotics is proceeding at a much slower pace than AI. And, to have like fully autonomous systems that can, say, dig up all the minerals necessary, transport them across the ocean to the necessary sites, manufacture the factories, make sure that there are electrical power generating stations, make sure that there fix any issues, fix the transmission lines when a storm occurs, like all this stuff. It's crazy. I just don't think that's going to be automated anytime within even my lifetime necessarily.
Yeah.
So far more likely is that AI would be symbiotic towards us. And I think in particular, as we move towards quote unquote super intelligence, meaning AI systems that can reason even better than we can, if anything, I think the chances are that AI would recognize, oh, I want humans to be helpful. I want humans to be alive. I want to interact with humans and have them work with.
Yeah, because without them, there would be no
Absolutely.
existence of the AI system. So
Absolutely.
it has to be yes.
Exactly. My bigger concern with AI, and maybe more broadly, and this is the only also way I also fear an extinction question, is not with super intelligent AI deciding to kill us, because I don't think that would happen for the reasons I just articulated, but instead with not so intelligent AI doing something awful. So here I would reference the movie Doctor Strangelove. I don't know if you've ever seen it.
No.
Okay, so it's a classic movie by Stanley Kubrick from the '60s, wherein this crazy American general. It's all too relevant nowadays. This crazy
Oh, what's it
American
called again? Doctor
Doctor
Strange Love?
Strangelove,
Okay,
yes,
I'll have a look at that.
and this crazy American general launches a nuclear strike against Russia,
Yeah.
uh, and then gets revealed that the Russians have built this doomsday machine that, in response to any attack from America, would immediately wipe out all life on Earth. And then the movie grows from this premise. But the point is that in this movie, the danger comes not from a super intelligent system, but actually from a really dumb system. The problem is that the Russians set up this really dumb system that no matter what, whenever it senses an attack, obliterates everything.
Okay.
And this is where I would fear potential downstream effects from AI is if people put AI systems in charge of, you know, deadly weapons systems, or even they just give them a lot of power to manipulate various other components of systems that could eventually be deadly. And they don't do a good job of actually ensuring that this AI is really thinking about its own best interests, let alone
Yeah.
humanity's best interests, but instead is kind of a stupid system, then you could have, yeah, awful scenarios occur.
Mhm.
Not to mention, of course, the possibility, and this is something Joshua emphasizes as well, of humans using AI to do nefarious
Of
things.
course, of course.
So there are all sorts of dangers with AI, and I don't want to downplay that. I think this is a very real concern. But indeed, the thing that I'm skeptical of is the idea that a super intelligence would just decide to wipe us out, because I don't actually see that as a plausible scenario.
Right. So I suppose then you're kind of helping alleviate this issue by first of all doing the research and trying to find out, the right kind of intelligence, making something actually intelligent. And on the same time, I don't know if I'm extrapolating a bit, but also you work a bit with different AI startups and
Yep.
AI consulting firms. So the Edgy Data Labs, Silico Labs, and Lamarck.
Yep.
Is that something that you're also trying to, because the real world impact of the AI system is that how you're trying to make sure it's safe used and
Yeah. So my work
offers
with
AI.
some of these startups and doing consulting for various companies has been less about safety, but more about just seeing the benefits of AI in a variety of areas of the economy. So we're at a kind of funny stage with AI right now where AI is getting really good. To anyone who hasn't interacted with the latest models, like, go give it a try. Like, honestly, like these systems are, you can have surprisingly intelligent
No,
conversations with them,
it's
and
incredible.
they can solve surprisingly complex problems as well.
Yeah.
Uh, so I have no doubt that AI has all sorts of potential benefits to the economy, but we're not seeing it yet because we're at this kind of funny stage where a variety of aspects of how we've set up our economy and our companies are not well built to actually using the power of AI.
Hmm.
Um, I'll give an analogy that the Economist provided, which I think is really interesting. So the tractor was invented like at the end of the 19th century, but it was only adopted in widespread form in the post-war era.
Hmm.
So why was there like a 50-year gap where tractors existed, but farmers didn't really use them all that much? And the answer is that when the tractor was first invented, the vast majority of farms were small farms run by individuals.
Hmm.
And the capital costs and hassle for, a farmer in 1905, farming some plot of land by themselves to bring in a tractor and do
Yeah.
it. Like, just was not worth it. Like, it didn't make
Yeah.
any sense for them. It would have cost them more money than they would have saved from it, especially given the size of land that
Yeah. I
they
mean,
were
is it
tilling.
actually that useful even if you do buy it?
Right,
You'd
exactly.
have to expand and
Yeah,
everything.
exactly. It only became reasonable to use tractors widely once you shifted towards industrial farming,
Right.
where you had, teams of people tilling huge plots of land. And I think there's going to be a similar thing with AI. So I think that in the case of AI, we have all sorts of different aspects of the economy where right now it would be hard for companies to incorporate AI into their workflows and
Mhm.
actually see financial benefit from that. Most of the time, it would probably cost them more money than they would actually save from incorporating AI.
Of course, yeah.
But I think that companies should start thinking about how things might change over the next little while, because if you restructure how your company works, then it might make a lot of sense to incorporate AI into
Mhm.
it. So, an example that I can give, one of the companies I work with, you mentioned, I'll give two examples for each of the startups that I advise right now. So one is the AG Data Labs. So they work with a lot of construction and logistics firms, trying to help them to use AI to improve their efficiency.
Mhm.
And it does require, both change to your workflows to some extent as a company in logistics or construction.
Yeah, there's definitely some constraints that you have to look at before you just throw AI at it.
Exactly. And also you have to be collecting data. Like,
Yeah,
your data has to be in a good
that's
format for
like
the
the
AI
number
to
one.
ingest.
Yeah, exactly.
That's right. And you have to figure out how you can actually take advantage of the scale that AI would permit. So like,
Mhm.
how can you actually turn this AI system into something that would benefit you at scale rather than just on a small bespoke project?
Right.
Um, Another example then is another company I advise, Silico Labs, is developing software for studying human behavior using VR and AR. And here again, I think there's huge potential for AI. So like when we think of, for example, market research, like it's crazy on some level that like we still basically use focus groups and stuff like that for determining what customers will want,
Yeah,
right? Like
yeah,
you bring in a group of people and you say, how do you like this product? Right.
yeah.
And like, that's bonkers. Like, we should be able to, through using the behavioral data you read off of VR or AR, while someone's like engaged in a virtual store or something like that, figure out from all of the subtle little behavioral patterns in their eyes and their hands and everything, what's actually effective.
Mhm.
People have done this on social media. That's effectively what they're doing, right? But you could expand this to a lot more if you incorporate this with VR and AR. So these are the sorts of ways in which I'm trying through my work as an advisor to help companies that are, in my opinion, trying to build out the tools necessary to actually make AI work for the economy in the near future.
For sure, kind of shortening that lag between, right, the invention or
Yes,
the discovery of this new technology and the actual
exactly.
implementation and fruits of the labor.
Exactly.
I mean, it comes from every like technical revolution you can think of. Like, there's always a lag, but I feel like with artificial intelligence, it's going to be a shorter, obviously, time lag than what it was for the tractors and the printing press and so
Yep,
on.
exactly.
So,
Exactly. And I think so, another area you mentioned, Lamarck Labs. I've had to step back for now as an advisor for them because of my role with Ivado, but uh, I I still interact with them. They're friends of mine, and they're building really important stuff. I
that was
think,
in neurotech.
yeah.
Yeah.
So this is, in neurotech, another area where I think AI could be revolutionary,
Mhm.
because brain activity patterns are incredibly complicated, and identifying
Yeah.
the signals within that could tell you something about someone's mental health, someone's mental state, the behaviors they're engaged in, etc., is an incredibly complex problem, but one which I think at scale, if we can throw compute at it and build foundation models on neural data, we could actually crack. But again, it requires some thinking about the infrastructure. How do you get data sets of neural activity that are big enough? And how do you get AI systems that can train across such diverse data as you would get from many different thousands of people's brain activity, for example?
For sure. Yeah. In a recent lab meeting at the Neuro, actually, yesterday, actually, we were looking over this paper using a whisper model to analyze different parts of the brain in relation to production, comprehension of
Mhm.
speech. And one of the lab members was like, okay, so like, what did we learn from this? Because there was no like neurological insight.
Right.
They've already known this stuff for years, but it was essentially like a proof of concept that you can, use these kind of models at scale and derive these kind of insights on a multitude of different data sets.
Right.
And then if it's, sophisticated enough and used properly, then yeah, you can like maybe discover some things and use it
Yep.
for good. So
Exactly. And I really do think that this will be key to actually seeing real world impacts from neuroscience. The fact is that neuroscience, despite the many billions of dollars that have been invested in neuroscience research over the last few decades,
yeah,
uh, we have a relatively limited number of examples like where it's had actual impact
yeah,
on either patients or consumers. And I think to change that will require AI.
that's a good point. And just coming back now, I don't want to take up too much of your time. We're nearing the end, but you've come from Toronto to Montreal now.
Yep.
Montreal is obviously a very big AI hub in the world and in Canada as well. How do you see, the ecosystem here developing? Is there some things that are still challenges that we have to break through? And then what would be the sort of solutions you want to see implemented?
So I think Montreal has a number of great cards up its sleeve. One of which the most important one is just the ecosystem of talent that's here. A lot of really really smart people are here in Montreal and or have connections to Montreal because it has been a center of both AI development and neuroscience development for decades.
Mhm.
Uh, so I think that that's our major asset. Um, the thing that holds us back, arguably, is we don't have the same access to capital that they do, say, in Silicon Valley.
Oh, for sure.
And this really changes the nature of being a startup in Montreal compared to being a startup in Silicon Valley. And
You hear
it's
about like funding situations. They're like, oh yeah, I'm going to raise like $1 million. Canada, that's like, okay, well, that's pretty good.
Yeah, I know exactly. Like $1 million for a startup in Canada is like, wow, congrats, good
Yeah.
work. In Silicon Valley, it's like, you guys really screwed up.
Yeah.
Like, what are you doing? Like this juice machine got $20 million. Why, like that's the scale of things. And I think so thinking about how we can build up an ecosystem of capital support for startups here. Now, so that's a critical question for us. Whether it should look exactly like it looks in the valley, I don't know. Maybe it can't. The reality is that a lot of this stuff in the valley is also driven by the insane market valuations of the various tech companies in California.
Mhm.
When you look at the American stock market, it's crazy how much money the tech companies from Silicon Valley are worth relative to uh, literally the rest of the American economy,
Yeah, I mean,
basically. Um, it's like half and half kind of
yeah,
thing,
yeah,
right? And I think that that's obviously a big part of it, which would be difficult to fully replicate in Montreal. But maybe what we can do is either attract some of that capital from Silicon Valley or think about alternative ways of financing this stuff, maybe in a more Canadian fashion somehow, that involves less, random crazy rich individuals willing to throw a lot of cash at something, and more careful planning and coordination with both people with capital in the private sector, but also with governments. I don't know exactly what that will look like. I hope, though, we can build out that economy here in Montreal because
Mhm.
I think it's really a unique city with a wonderful, rich heritage in AI and neuroscience, and I would love to see it really not only keep its status in terms of scientific research globally, but also shift into being a major economic center for AI.
For sure. I hope to see that happen. But obviously, the Mila is a great place to start.
Yep.
And your research as well. Like, where can we follow what you're doing and the initiatives you're taking?
So you can always look at our lab website, though I'm not the best at keeping it up to date. The easiest way to follow what I'm up to is to follow my social media accounts, in particular on Blue Sky. I'm quite active. I stepped back from Twitter a little bit because I'm feeling disgusted with Elon Musk and his antics. But if you follow me on Blue Sky, we announce all of our research there, and more broadly, I try to engage with the research community at conferences and stuff like that. And you can always find me at various conferences and workshops where we present our work.
That's wonderful. But thanks so much for the time. Very insightful. I'd have to go get back to you on the question of why the elephants and the dolphins are more intelligent than us. It sounds very interesting.
Oh yes, that'll be a conversation for another
Yeah,
time.
for
Quite.
sure. But until then, super insightful. Thank you so much.
Thank you for having me. It was a fun conversation.
My pleasure.
Cheers.